Welcome back. Today, we're unraveling an absolute masterclass of a cosmic mystery. When we look up at the night sky, it's so easy to just trust our eyes. We see these clusters of stars strung together, forming brilliant shapes, and our brains naturally assume, hey, they must be deeply connected. But space is tricky. In this explainer, we're going to decode a stunning visual illusion known as the False Comet cluster. We'll be digging into some fresh data that completely pulls back the curtain on this stellar neighborhood, and together, we're going to find out what's really going on in the dark.
All right, let's dive right into this. Meet the breathtaking Prawn Nebula, officially known in the catalogs as IC 4628. This glowing, gorgeous landscape is nestled within the constellation Scorpius, specifically located out in the Sagittarius Carina arm of our Milky Way galaxy. It's incredibly beautiful, and it's a key piece of the string of open clusters that we collectively call the False Comet. But as stunning as this view is, it's actually hiding a massive secret about how these stars are truly relating to one another. So here's our flight plan for this explainer. 1. The False Comet illusion. 2. Zooming in on the tail. 3. The 3D mapping revolution. 4. A tale of two families. And 5. The dynamic Milky Way.
Section 1. The False Comet illusion.
Well, the fundamental problem we face as observers down here on Earth is entirely one of perspective. Space is obviously inherently three-dimensional, but our view? It's essentially flattened into two dimensions. When we look at a string of objects like the False Comet, which includes the Prawn Nebula, Trumpler 24, Collinder 316, and Caldwell 76, they look for all the world like a cohesive, interacting family of stars forming a comet-like shape. So the central mystery we are unpacking today is this. Is this string of clusters an actual physically bound structure in space, or is it just a clever line of sight trick?
Section 2. Zooming in on the tail.
The anatomy of this specific tail region is absolutely fascinating. Located in the Scorpius constellation right within the Sagittarius arm, the tail is primarily made up of the glowing gas of the Prawn Nebula, a sparse open star cluster embedded deep inside it called Trumpler 24, and another cluster known as Collinder 316. Now historically, this area has been incredibly difficult to map precisely. Why? Because there's a lot of gas irregularly distributed here, which causes significant differential reddening. Basically, cosmic dust distorts our view of the star's true brightness and their colors.
And this brilliantly illustrates exactly where we are looking today. Recent astronomical data specifically targeted a 1 square degree zone centered perfectly on this tail region. Researchers zeroed in on this zone because it is exceptionally rich in pre-main sequence stars, which are essentially infant stars that are literally still forming.
This entire neighborhood sits within something called the Scorpius OB1 association. In astronomy, a stellar association is a loose, unbound group of young stars. They aren't held together by gravity as tightly as a dense cluster is, and they're usually interpreted as the early stages of a star cluster's dissolution. Think of it like a graduating class. They were born together, but they'll slowly drift apart over time.
So knowing that this is a loose association, it brings us right to the ultimate detective question for the stars in this tail region. Are they truly a family born from the exact same molecular cloud, or are some of them just strangers passing in the dark, perfectly aligned from our earthly vantage point?
Which leads us to Section 3, the 3D mapping revolution.
Astronomers tackled this exact mystery by combining two incredibly powerful datasets. First, they gathered fresh optical photometry data. This means they looked at different wavelengths of light to assess the exact colors and brightness of the stars. Second, and this is a real game changer, they cross-correlated that data with the Gaia DR2 space observatory. Gaia provides highly precise astrometric data. By combining these two things, researchers were able to map the stars in 5 dimensions: their 2D coordinates on the sky, their parallax, which gives us distance, and their proper motion components. They then fed this massive 5-dimensional dataset into a clustering algorithm called DBSCAN to mathematically prove which stars actually belong together.
Let's quickly define proper motion, because it's the absolute crucial clue here. Proper motion is the apparent angular motion of a star across the sky over time. Because stars are physically moving through space, measuring their proper motion allows astronomers to essentially track their trajectories. It makes sense, right? If a group of stars is truly a family, they should be moving through space together in roughly the same direction and at the very same speed.
Using these incredibly strict parameters, researchers managed to cross-match and keep only the stars with highly accurate parallax data. That left them with exactly 11,506 objects to analyze. That is an enormous amount of high-quality data used to crack this case.
Now, what's really interesting about this slide is how we visualize that massive data set. The algorithm identified 7 distinct physical groups, which you can see color-coded on the left. On the right, the spatial density map reveals the actual physical shape of this star-forming region. We aren't just looking at a flat 2D picture anymore, we're seeing the distinct physical clumps of stars that actually share real estate and movement in space.
Section 4. A Tale of Two Families. When astronomers looked at the ages, distances, and proper motions of these 7 groups, a pretty shocking narrative emerged. So, the crucial point is that those groups actually belong to 2 completely different families. Family I is packed with young, pre-main sequence infant stars. They form this arc-like structure stretching right through our False Comet tail, and that includes the Trumpler 24 cluster. They are definitively native to the Sco OB1 association. But Family 2? Entirely different story. This group is made up of much older stars, including a cluster known as VdB-Hagen 202. Crucially, they have a completely different proper motion. They are moving at a totally different speed and direction. They are absolutely not native to this young stellar nursery.
To confirm just how young Family I really is, researchers looked at infrared data from the WISE telescope. Because these infant stars are just so young, many of them still have contracting envelopes and transition disks of dust and gas swirling all around them. This infrared data perfectly highlighted these young stellar objects, completely confirming that Family I is indeed a very real, very active, recent star-forming event.
And their distance is unified too. 1,560 parsecs, or over 5,000 light-years, is the average distance from Earth to these young Family I stars. This proves definitively that the stars in Trumpler 24 and the surrounding area are indeed clumped together in the exact same physical neighborhood in 3D space.
But what about Family 2? Well, the researchers came to an absolutely amazing conclusion, stating, quote, VdB-Hagen 2002 do not belong to the association, but are caught in the act of passing through it. Think about how wild that is. This older cluster of stars is literally just a cosmic stranger. It is caught driving right through the background of our False Comet picture, totally photobombing the younger stars.
Let's move to this chart and see how all this builds together. Plotting the brightness and colors of the Family I stars on a color magnitude diagram really seals the case. Those dashed lines? They're theoretical models called isochrones. You can see how perfectly the black dots of our observed stars align with the models for a very young stellar nursery. The math, the movement, and the brightness all perfectly agree. Family I is native, and Family 2 is just passing through.
Finally, Section 5. The Dynamic Milky Way.
So, what does this highly specific investigation teach us about our galaxy as a whole? Here are the big picture takeaways you should remember. First, space is incredibly dynamic and layered in 3D. Our 2D view from Earth can easily hide cosmic photobombers, like VdB-Hagen 22, behind visual alignments. Second, the incredibly precise astrometry from the Gaia mission is completely revolutionizing how we map stellar nurseries, allowing us to definitively separate fact from optical fiction. And finally, the False Comet is a beautiful paradox. While the comet shape itself is an illusion caused by unassociated stars passing in the night, the tail region of Trumpler 24 and the Prawn Nebula is a very real, highly active, and deeply connected arc of young, forming stars.
It kind of makes you look at the night sky completely differently, doesn't it? If the False Comet has been hiding a cosmic photobomber this entire time, it begs the question, what other famous, familiar structures up there are just waiting to be exposed as illusions by 3D mapping? Keep looking up, keep asking questions, and I'll catch you on the next explainer.